Hello, students. Very good afternoon. My name is Ravi Ranjan Kumar, and I welcome you all to this fourth session in the series of the lectures of rotational dynamics. Okay, so in today's class, we will be covering combined translational and rotational motion. So, without losing any time, let me share my screen with you people. Okay, so here we go. So, combined translational and rotational motion. So, in order to study the combined translational and rotational motion of a rigid body, we need to understand two things. Okay. The first thing, that combined translational and rotational motion, CTRM, we will be using this word for combined translational and rotational motion. So, CTRM of a rigid body can be treated as combination of purely translational motion of rigid body and purely rotational motion of rigid body about an axis passing through its center of mass. Okay, so we have learned how to deal with purely translational motion of rigid body. In case of purely translational motion, each and every point on the rigid body will be moving with same velocity, and that will be equal to velocity of center of mass. We are very well aware that how we can write the expression for kinetic energy, angular momentum, linear momentum in that case of purely translational motion. And similarly, we have also studied how to treat the purely rotational motion of a rigid body, that is about a fixed axis. Okay, so we in that case also we know that how to write the kinetic energy and angular momentum, etc., for that rigid body. So whenever we are discussing combined translational and rotational motion, we must bifurcate the motion in two parts. Okay, and one part would be purely translational motion, and the another part would be purely rotational motion of rigid body about an axis passing through center of mass. And before moving ahead, the another thing we need to understand is that the angular velocity omega, or angular acceleration, alpha, of rigid body with respect to any point on rigid body will be same. So we have already seen and justified this result in very first lecture of rotational mechanics. So we will be using that. So about any axis of rotation in the frame of the rigid body, the angular velocity or angular acceleration is going to be same. So we need not say that angular velocity of rigid body is about this axis or that axis. So about any axis it is going to be same. So once we are done with these two things, now we are ready to deal with the motion of rigid body in combined translational and rotational form. Okay, so uh, proceeding first with the velocity. The first thing we are going to do is we are going to have an expression for the velocity of any point on the rigid body. So velocity of any point on the rigid body Vp can be written as velocity of point C with respect to center of mass plus velocity of center of mass itself. So that is the vector form of velocity of any point P on the rigid body. And velocity of point P with respect to C, uh, since it is so this would be the rotational form, so that would be, you can say, the rotational form of the velocity, and this would be nothing but translational form of the motion. So let me give you one example, one very simple example we are going to take. So let's say we are having a rod of mass m and length l. Okay, and let's say this is uniform, so at the midpoint there would be its center of mass is here, so this is point C. Let's say point C is moving with some velocity v naught, and at the same time it is undergoing rotation with angular velocity omega. So here I have said, like, the angular velocity about an axis passing through center of mass is omega over here. So if we know these two things, okay, so what we will be able to do, we will be able to find out the velocity of any point on this rigid body. Let's say, for example, this point, the topmost point is point A, and let's say the bottommost point is point B. In this combined translational and rotational motion of this rod, we are interested in finding out the instantaneous velocity of point A as well as point B. Okay, so point A, so translational form, the Vt thing, the velocity of any point on the rigid body due to the translation of this rod over here is going to be same. The velocity of any point is going to be same. So every point will be having v naught and v naught translational velocity, which is equal to the velocity of center of mass. And apart from that, in the center of mass frame, this whole thing is undergoing uh, purely circular motion. Like point A will be moving along a circular path, point B will be moving along circular path. So if we look, like, due to rotation, the velocity of uh, point A would be in forward direction, that is tangential also, and that will be equal to L by 2 times omega. And the velocity of point B here would be in tangential but backward direction, and that would be L by 2 times omega. We are using V is equal to R omega formula. So being said that, what we have got, like, velocity of point A will be equal to the vector sum of the velocity due to translation and velocity due to rotation. So that they are in same direction, so we will be able to write that would be v naught plus L by 2 omega. And similarly for point B, vb will be the vector sum of velocity due to translation plus velocity due to rotation, and here they are in opposite direction, so we will be able to write v naught minus L by 2 omega over here. So so we have just got the velocity of the endpoints, but using the similar method you can get the velocity of any point on this rod over here. So now let's take another example, okay, which would be describing this fact more clearly. So let's say we have a round body, okay, and let's say it is rolling on the surface. So let's say this is its center of mass, so its velocity is v naught, and it is rotating with angular velocity omega, which is equal to v naught by r, let's say. So now we are interested in finding out the velocity of, let's say, this point P. Okay, and this point P here is making an angle theta with the vertical direction. We are interested in finding out the velocity of point P on this round body. So again, we are going to use this formula, that velocity of point P will be equal to velocity of point uh, P with respect to C plus velocity of c over here. So that is basically translational form of velocity, and this is rotational form of velocity. So due to translation, the velocity of this point is going to be same as the velocity of center of mass. So this is going to be v naught, and due to rotation it will be having a tangential velocity, and that will be equal to nothing but r omega. And r omega's value, when we will substitute this value of omega, that will be equal to v naught as well. Now looking into the geometry over here, so if this angle is theta, this angle is going to be theta, and this angle here is also going to be theta. So velocity of this point P, velocity of point P is vector sum of this translational form of velocity and this rotational form of velocity, and they are having equal magnitude, but the angle between them is equal to theta. So the resultant velocity here is going to be along its angle bisector, and this would be the velocity of point P. Okay, so when we will be looking at its magnitude, we already have a simple formula. So that will be giving us 2v naught sine theta by 2. So that is the velocity of point P. So similarly, just to have a better insight to this problem, let's say 4 points let's have. Let's say this is point A, this is point B, this is point C, let's say this is point D, and this is point E. So what would be the velocity of point D using the same expression? The velocity of this point D is going to be 2v naught. The velocity of point A will turn out to be equal to 0. Velocity of point B will turn out to be in this direction, and that would be equal to root 2 v naught. And the velocity of point E will turn out to be in this direction, that would be root 2 v naught. This angle here is 45 degree as well, this angle here is 45 degree as well. So the idea is we can get the velocity of any point on the rigid body if we have the information that what is the velocity of center of mass and what is the angular velocity of the rigid body about an axis passing through center of mass. So this is how we can write down the velocity. And next thing we will be looking at it is about the acceleration. We can deal with the acceleration using the same concept, but we need to be a little bit more careful while dealing with this for some obvious reason which is going to be clear. So let's say acceleration of any point P will be equal to acceleration of C plus acceleration of point P with respect to C. So this is the vector form of acceleration of point P. So acceleration of point C. So this will be the translational acceleration, you can say. That would be same as the acceleration of center of mass. And this would be the rotational form of acceleration. So if we assume that a point is undergoing circular motion about its center, then any point will have two components of acceleration, and that would be tangential as well as centripetal over here. So let's say let's take one very simple example. Let's say this is a round body over here, okay, and this is undergoing combined translational and rotational motion, and this has acceleration a naught, and let's say its angular acceleration is alpha, and at the same time we have information about angular velocity omega also. So these are the parameters we are having over here. So for example, we are interested in finding out the acceleration of any point P. Let's say this point P over here. So this can be treated as the combination of purely translational and purely rotational motion. So if we consider the translational motion, okay, so since the acceleration of this point is a naught, so in purely translational motion, let's say purely translational motion, the acceleration of this point P here would be a naught as well. Okay. And plus we will combine vectorially add with another motion, that would be a purely rotational motion of this body about an axis passing through center of mass. So this is rotating with angular velocity, angular acceleration alpha and angular velocity omega, and so this point P over here will be undergoing purely circular motion. So it will be having two components of acceleration. This would be, let's say, AT, and this would be nothing but AC over here. And obviously, the value of AT, we already know that will be equal to R alpha, and the value of AC would be nothing but omega square R. So when we will be combining these two motion, purely translational motion and purely rotational motion, we are ready to write the net acceleration or the resultant acceleration of this point P over here. So it will have one uh, component of acceleration due to translation. So that is A naught. Let's say this is A naught, and we will be having a tangential component, so that would be AT, and we will be having a centripetal component AC. So in ground frame of reference, like in ground frame, the acceleration of point P, the acceleration of point P is going to be vector sum of all these. So like this is A naught, so which is acceleration of center of mass, and acceleration of point P with respect to center of mass is going to be AC plus AT. And let me again write the expression for AC and AT. So AC is nothing but alpha cross R, sorry, AT is alpha cross R, and AC is nothing but minus omega square R. Okay, so this is how we are going to write the acceleration in ground frame. Let's take one simple example over here. Let's say, for example, again that round body we are taking. Okay, and it has acceleration A naught, and alpha is, say, uh, A naught by R, and there is some omega also. Okay, so the acceleration of this point, if we try to find out, so due to translation, it is going to have acceleration A naught. Okay, and due to rotation, its acceleration will be having a tangential component, and that would be R alpha. So this will turn out to be A naught as well, and this component is going to be omega square R. Okay, so effectively this will be having acceleration of, let's say, this point is A, so acceleration of point A will be nothing but the resultant of this and this. Okay, so that would be, let's say, 2A naught square plus omega square R whole square under root, etc. If omega is equal to 0, it is simply going to be 2A naught. And for instance, here the acceleration of this point, let's say this is point B, so A naught, the translational form of acceleration due to a motion of center of mass, will be in this direction, and this would be the tangential component of acceleration in C frame, so that is going to be A naught as well. So it will be simply omega square R, because this and this will get cancelled. So acceleration of point B is going to be towards the center. So that is how we can find out the acceleration of any point on the rigid body if it is having combined translational and rotational motion. So now let's discuss uh, like how can we write the expression for kinetic energy of rigid body in combined translational and rotational motion. Okay, so we have been already saying that the kinetic energy of any system of particles can be written as kinetic energy of the system of particles in C frame plus like half times total mass of the system into velocity of center or speed of center of mass square. So we have already learned and derived this expression in previous classes. Okay, so basically this k term over here, so here what we are having, the motion of rigid body about an axis passing through center of mass or in C frame is of purely rotational form. So this we can say that this would be the rotational form of kinetic energy, and this would be the translational form of kinetic energy. And rotational form of kinetic energy, simply we can write it as half into uh, moment of inertia about center of mass into omega square. We have learned how to write the kinetic energy of a rigid body if it is in purely rotational motion, and this would be simply half mvc square. So we will be using this formula in order to find out the kinetic energy. Let's say, for example, uh, we have a, say, round object which is undergoing, say, purely rotational motion, so v naught, and its omega is nothing but v naught by r, let's say. And let's its moment of inertia about center of mass IC is something like mk square, depending upon whether it is a ring, disk, a hollow sphere, solid sphere, the value of k would be different, and its radius is, let's say, r. Okay, and its mass is m and radius is r. So we wish to find out the kinetic energy of this rolling around body. So k would be equal to translational form of kinetic energy plus rotational form of kinetic energy. So translational form of kinetic energy is going to be simply half m v naught square, and rotational form of kinetic energy is going to be half into I would be over here, that would be mk square, and omega, we have already, omega square will be v naught square by r square. So that would be like half m v naught square, you can take common, into 1 plus k square by r square over here. So that would be the kinetic energy of the rigid body in combined translational and rotational motion. So you can also see, so in this kinetic energy, some part of it is in translational form and some part of it is in rotational form also. So we can also find out this ratio, like what would be the fraction of kinetic energy in translational form and what would be the fraction of rotational energy in uh, total. So this quantity we can find out. So kt by k is going to be simply 1 divided by 1 plus k square by r square, and this quantity is going to be k square by r square divided by 1 plus k square by r square. So for example, if this is a, for example, this body, say, is a hollow sphere, let's say this is a hollow sphere, so in that case the value of k square by r square will turn out to be 2 by 3, because we know the moment of inertia. So this denominator 1 plus 2 by 3 would be 5 by 3, so this will turn out to be uh, 3 by 5, and this will turn out to be 2 by 5 over here. So 1 plus 2 by 3, that is 5. Okay, so this is this is the fraction we are having. One simple thing, like for example, in the same question, if I ask, let's say, if somebody is asking us, like, what would be the kinetic energy of only the upper half of this, let's say, hollow sphere, okay, at this instant, what would be the kinetic energy of the upper half only? So how will we deal with this problem? So let's try to figure out this thing. So this is the whole hollow sphere, say its mass is m and radius is r, and this is undergoing rolling motion, so this is v naught and this is omega, which is equal to v naught by r, and we here are only interested in finding out the kinetic energy of the upper part of the sphere. Okay, so the kinetic energy for any the upper part of the sphere is also undergoing combined translational and rotational motion. So again, kt plus kr we can write. So kt is nothing but half mass of the let's say mass of the upper half, that would be say m by 2, into the velocity of center of mass of the upper half. So vc square we will be writing, and that kinetic energy in rotational form would be half into the moment of inertia of the upper half with respect to its center of mass into omega square, and omega we already know. So we need to first find out, let's look at it, we need to first find out what would be the value of vc. So value of vc is the velocity of center of mass of the upper half of this sphere. Okay, so the center of mass of this upper half is going to be somewhere here, and we have already learned this formula in the class of center of mass. So for a hollow hemisphere, the center of mass will lie, so this thing is going to be r by 2. So this is the center of mass of this. So let's say this point is o. So moment of inertia of this hemisphere, hollow hemisphere, about o, like io, we know that will be equal to, this is a hollow hemisphere, so that would be its mass times um, you can say 2 by 3 uh, and r square about o. So that is m by 2. And using parallel axis theorem, we will be able to get this quantity ic over here. So ic is going to be equal to m by 2 is its mass, and that would be 2 by 3 r square. That would be, this thing is the moment of inertia about o. So about center of mass we need to subtract this r by 2 whole square thing. So this would be giving this quantity over here. Vc, how we are going to find out? So vc, so this you understand, this velocity of point c we have learned in the very first part of this lecture only. Due to translation, this will be having velocity v naught, and due to rotation it would be having velocity as equal to r by 2 times omega. So this will turn out to be v naught. So here we can clearly see that vc will be equal to 3 v naught by 2. So if we substitute the value of vc as 3 v naught by 2 over here, and the value of ic here we substitute from here, and omega we already know about any axis, even about this axis we learned, that is going to be v naught by r over here, that is going to be same. So when we will be substituting this value, we will be able to get the kinetic energy of the upper half of the body. In fact, using the similar methodology, we can find out the kinetic energy of any part of the rigid body. What just we need to understand, like whatever part of the body we are looking at, where is its center of mass, and what is the velocity of the center of mass of that part, let vc, and what is the moment of inertia of that part about an axis passing through the center of mass of that part only. So that is ic. So if we are able to get these quantities, we will be able to find out the kinetic energy of that part as well. So let me look at one more interesting problem over here of kinetic energy. Um, generally people commit mistake in this type of question. So let's say we have a rod of mass m and length l, okay, which is hinged at this point, and it is free to rotate about this axis. Okay, and let's say a disk, uniform disk of mass capital M and radius r is rigidly clamped at this end of the rod. So this is the rigid body over here, and let's say this whole setup is undergoing rotation or purely rotational motion about this point over here. So this is basically, let's say, omega the direction is this, and its magnitude of angular velocity is this. So what would be its kinetic energy? So I have chosen this problem because while dealing with this problem, many people seem to forget one aspect of this question we will very soon learn. So kinetic energy over here of this thing, K, is going to be the translational kinetic energy. Or first of all, let's write it as kinetic energy of rod plus kinetic energy of disk. One by one we will be writing. So writing down the kinetic energy of rod is real simple task, because the rod is undergoing purely a rotational motion over here. So its kinetic energy would be equal to half, and its moment of inertia about its end is going to be ml square by 3 into omega square over here. So that is kinetic energy of the rod. The real challenge here is to write the kinetic energy of the disk. So kinetic energy of disk, now you see, can you say that the disk is undergoing only translational motion? You see, like this is how along this path the center of mass of this disk will be moving. So the center of mass of this disk is moving curvilinearly. So the velocity of the center of mass of the disk is basically, you can say, uh, that would be equal to L omega. But can you see that this, apart from moving curvilinearly, okay, this disk is rotating as well. So now you just have to realize, let's say for example, at this instant this is some point A. So when this rod has come over here, so this disk would be somewhat like this, and this point A will come here if it is rigidly clamped to this rod. So now you see the orientation of this disk has changed. The point A has moved from here to here. That means the angular displacement is 90 degree. So the angular displacement of whole setup, when it is 90 degree, the angular displacement of point A is also 90 degree. So we can say that this disk is also rotating with same angular velocity omega. So you have to realize the motion of this disk is curvilinear translational motion, plus it is also rotating about its own axis with same angular velocity omega. So whenever we are writing the kinetic energy of disk, we will be writing the translational kinetic energy of disk plus rotational kinetic energy of disk as well. So translational kinetic energy of this would be half into m, and the velocity of center, its center of mass, we have already established, that is L omega square, and the rotational part would be like half, and I, you can say, is I would be simply mr square by 2 here, and omega here is simply same omega square, you can say. So kinetic energy of rod we have got, kinetic energy of disk we have got. So adding these, we will be getting the kinetic energy of this whole thing overall. So this is one problem. So we have learned how to write down the kinetic energy of a body in combined translational and rotational form. So now the another thing I want to discuss over here is about the angular momentum. Angular momentum. So when we were discussing the angular momentum of a system of particles in the previous class, we learned about this relationship, that angular momentum of a rigid body about an axis or system of particles, in fact, so about an axis passing through any point P, or simply just so that would be basically, or let's not write this subscript right now, or simply about origin, let's say origin we are writing. So whichever point we are looking to find out, about which the angular momentum we are finding out, we will treat that as our origin. So this expression was the angular momentum of the system of particle in C frame plus the mass, the total mass of the system of particles m into the position vector of the center of mass with respect to origin cross velocity of center of mass. So we have learned about this expression in previous classes. Okay, so this is the expression. So basically this term you can say this is the this is the rotational form of the angular momentum, and this would be nothing but the angular momentum of the rigid body about an axis passing through center of mass, and this is the angular momentum component due to translation. So this is related to the motion of center of mass, uh, because this RC is the position of center of mass and this VC is the velocity of center of mass over here. So this RC is the position vector of center of mass with respect to the origin. So in order to get it more clearly, let's look at one simple example over here. So let's say we have a solid cylinder of mass m and radius r, and let's say this is rolling as well. So this is v naught, and there would be omega which will be equal to v naught by r. So this is undergoing purely rotational motion, and let's have some coordinate system associated with it. So let's say this is x-axis and this is y-axis. Let's say this is origin, and let's have different points here. So let's say this point is A, this point is B, this point is C, and say let's have some other points. This point is D and this point is say E. So we wish to find out the angular momentum of this rolling solid cylinder about different points. So about whichever point we want to find out the angular momentum of this system, this rotational form, this angular momentum of this rigid body in center of mass frame, and we know in center of mass frame the angular momentum of the rigid body is not going to depend upon the choice of point. So this quantity is going to be same in each and every case. So it would be better for us to find out this quantity, L tilde, or you can say that would be L R as well, the rotational form. So what would it be? So due to rotation, if we assume, so this is uh, undergoing purely rotational motion about center of mass. So the formula we will be applying is simply I omega. So the moment of inertia of this solid cylinder is nothing but mr square by 2, and omega is nothing but v naught by r. So this gives us the magnitude, and direction wise if you look, so direction is the sense of rotation here is clockwise. So direction definitely is the inward direction, which would be along minus k cap. So simplifying this will be giving us mr v naught by 2 into minus k cap. So this part will be common to all the points. So now see, for example, do we see any points about which this translational form of angular momentum is going to be equal to 0? So yes, definitely we are having. So about point C or about point D, the R is equal to 0. So the translational form of angular momentum about an axis passing through point C or point D is going to be equal to 0. So LC is going to be equal to LD, and since this component has become 0, so this is going to be L tilde only, and that will be equal to mr v naught by 2 minus k cap over here. So this is about C, and about D we have already found out. And now when you will be looking, you can see the angular momentum of this solid cylinder, about point A and about point O are going to be same, because the difference would be the translational component. So MRC cross VC over here, when we are writing the magnitude, that would be M R perpendicular into V naught. So R perpendicular with respect to A and with respect to, in both the cases, it is basically equal to R, and it is having same direction as well. So in that case, the angular momentum about point O or angular momentum about point A are going to be same first of all, and that is going to be L tilde, which is already mr v naught by 2 minus k cap, and we are looking for the another component, so plus we can say, and its magnitude is going to be simply m r perpendicular is r into v naught, and its direction is also inward, so that is going to be minus k cap over here. So this collectively will give us 3 by 2 mrv naught along minus k cap. So that is angular momentum about O and A. So similarly, we can say the angular momentum about E and about B are going to be same, and that would be equal to L tilde, which is again mrv naught by 2 minus k cap. Okay, and the rotational form over here, like about point B, you can see the magnitude would be simply mr v naught, only the magnitude of angular momentum, and it is undergoing about this point P. This is undergoing anti-clockwise rotation over here. So anti-clockwise, that means it would be having a direction as k cap. So combining them, it will be simply giving you mrv naught by 2 k cap. So that is how you can find out the angular momentum of any rigid body about an axis passing through center of mass. The idea we have used is, again, the motion can be treated as purely translational motion of its center of mass plus purely rotational motion of the rigid body about an axis passing through center of mass. And being said that, let me discuss a very important concept over here. So which is known as the concept of instantaneous center of rotation. Instantaneous center of rotation, or you can say in short ICR, simple. So ICR basically is a point uh, in the frame of rigid body, you can say, which is instantaneously at rest. Okay, so if a point is instantaneously at rest, so if we consider the motion of the rigid body about that point, okay, so the motion of rigid body is going to be purely rotational. Okay, so it is like we are often interested in finding out the instantaneous center of rotation, and we will be looking at its application also. Let's take one simple example, like how are we are defining ICR. So let's say we have a body, okay, and we know the velocity of any point on that rigid body. Let's say this is point P, and its velocity is simply, let's say, Vp, and the angular velocity of this rigid body is omega. So about point P also it will be omega over here. So in order to find out the instantaneous center of rotation, what we are going to do is we are going to draw a perpendicular line passing through point P. Like this angle you can see is 90-degree. So somewhere on this line we will be having some point, let's say A. Okay, we will be able to write down the velocity of point A over here, as we have learned the how to write the velocities. Like you can use this formula, that velocity of point A will be vector sum of velocity of point P plus velocity of point A with respect to point P. This expression we can use. So velocity of point P is Vp, and the velocity of point A with respect to P will be due to rotation. And let's say if PA distance is x, so due to rotation its velocity will be in opposite direction, and that is going to be x omega. So velocity of point A, its magnitude, you can simply write that would be Vp minus x omega. So for this point A to be instantaneous center of rotation, VA got to be equal to 0. So solving that x, we will be getting as Vp by omega. So we have managed here to find out the instantaneous center of rotation. This is nothing but instantaneous center of rotation. And the benefit of finding out this point is now we can treat the motion of this whole rigid body in purely the motion of this whole rigid body about point A will be of purely rotational form, and this rigid body will be rotating with angular velocity omega about point A over here. Okay, so that means any point if we are having over here, so with respect to instantaneous center of rotation, this will be moving with uh, r omega velocity. So this is how we can find out the instantaneous center of rotation. Some other method of finding out the instantaneous center of rotation is, let's say for example, we have a rigid body and somehow we have found out the velocities of any 2 points, let's say point A and point B on the rigid body. Let's say velocity of point A is in this direction, this is VA, and the velocity of point B, let's say, is in this direction, VB. So we have already learned that in the instantaneous center of rotation is going to lie somewhere, let's take the B point somewhere here. So instantaneous center of rotation is going to lie on the line perpendicular to VA passing through A, and let's say this is point B over here. So the instantaneous center of rotation is going to lie on this line as well. So collectively we can say the instantaneous center of rotation is going to be located at the intersection of these two perpendicular lines. So this is basically ICR. So basically what we can say, that we can assume this to be rotating, undergoing purely rotational motion about ICR, let's say with omega. And how we can relate, let's say this is some RA and this is some RB over here. So VA, the magnitude of this would be nothing but RA into omega, and VB, the magnitude of this would be nothing but RB into omega. So if we are able to locate the instantaneous center of rotation, so if we manage to find out the instantaneous center of rotation, writing down the kinetic energy of the body, kinetic energy of the rigid body, it becomes very, very simple. So since it is, we are assuming that it is undergoing purely rotational motion about instantaneous center of rotation. So this will be half into moment of inertia of the rigid body about the instantaneous center of rotation into omega square. So this is how we will be able to write the kinetic energy of the body in alternate way. So one simple question we will be looking at, and we will try to use the concept of instantaneous center of rotation in order to solve that question. So let's say this question is, for example, we have a smooth horizontal surface and we have a rod of say mass m and length l. Okay, and this rod is slightly disturbed, okay, so that it starts falling. Okay, so falling means since there is no horizontal uh, friction on this rod, so we have already learned the kinematics of this situation, that its center of gravity or center of mass will be following a linear path. It will be moving along a linear path. So at a later instant, okay, let's say at later instant the center of mass is here. So at that time, let's say its orientation would be something like this. Okay, and let's say this angle at this instant is equal to theta, and here we are having its center of mass. So at this instant theta, we are interested in finding out the angular velocity of the rod. We are interested in finding out the angular velocity of the rod. So how are we going to do that? So when we are required to find out the angular velocity of the rod, the best way will be to use principle of conservation of energy. So that will be delta U plus delta K is equal to 0. So finding out the change in potential energy is easy. So but when we are writing the change in kinetic energy, so initial kinetic energy is obviously equal to 0, and at this instant the final kinetic energy we are to find out. So final kinetic energy, if we treat the motion as combined translational and rotational motion, it will be having two parts of kinetic energy, rotational as well as translational. But if we consider the concept of instantaneous center of rotation, and if we are able to write the kinetic energy of this rod about an axis passing through instantaneous center of rotation, I will be using only formula half I omega square. So before that, we need to find out the instantaneous center of rotation. So now see, we have just learned that if we are able to figure out the velocity of any 2 point on the rigid body, so here the velocity of point C is in this direction, and this end of the rod is constrained to move only along the horizontal. So the velocity of this point is in horizontally rightward direction. So we are drawing a perpendicular passing through point C, and let's say this end is A and this end is B. So a line perpendicular to velocity of point A and passing through A. So this here is instantaneous center of rotation. So obviously this length is equal to L by 2 cos theta here, and this length here is equal to L by 2 sine theta. Okay, so we are interested in finding out, like that would be delta U plus delta K is equal to 0. So potential energy is decreasing at the cost of which the kinetic energy is increasing. So delta U, we can simply write it as like M times G into the change in height of the center of gravity. So previously center of gravity was L by 2 height from the ground, and now it is at L by 2 sine theta height from the ground. So that would be mg L by 2 into 1 minus sine theta would be decrease in potential energy, and that will be equal to uh, the change in kinetic or increase in kinetic energy. So that would be equal to half into the moment of inertia of this rod about instantaneous center of rotation, and that is going to be using parallel axis theorem about C. It would be ml square by 12, and from this the distance between these two parallel axes would be m, and that would be L square by 4 cos square theta over here. So this is the moment of inertia. Okay, and that multiplied with the omega square, let's say here about this, it is undergoing purely rotational motion, so this would be omega square over here. So solving this equation, we will be able to get the value of omega here. So once we get the value of omega, okay, we will be able to find out the velocity of each and every point on the rod, just we have learned. Okay, so this is how we can deal with this problem. One another interesting aspect of this problem I want to discuss with you, since we are dealing with the mechanics of the sliding rod. Let's discuss it over here only. So let's say this rod has left to slide, and this surface is frictionless, and this rod will have this orientation here. Okay, at any instant, let's say this is theta. Okay, so here now this time we are interested in like finding out like what would be the acceleration of its center of mass. Let's say this point is A, this point is B, and this point is C. So what would be the acceleration of its center of mass? We have already said that the acceleration of its center of mass will be directed in vertically downward direction, and at the same time we are interested in finding out that what would be the angular acceleration of this rod over here. So how are we going to deal with this problem? So let's look very, very closely. So first thing, like we need to find out the omega of it. So in the previous problem, we already managed to find out the angular velocity of this rod at this instant over here. Okay, so now see, again the motion of this falling rod can be uh, uh, can be resolved in two parts. Like one would be the acceleration of center of mass in C frame you can say, and the another would be purely rotational motion in center of mass about an axis passing through center of mass. So let's draw the diagram again. So this is the rod and this is the center. Okay, so the acceleration of center of mass is this. So due to translation, the acceleration of any point is going to be in same direction. So let's look at this point A. So the acceleration of this point A due to translation is going to be in this direction over here. Now, like about this point P, this is undergoing a purely rotational motion with angular velocity omega and angular acceleration alpha over here. So this point is going to have, due to rotation, it is going to have a translational component, tangential component over here, that is at will be equal to L by 2 times alpha, as well as it will be having a centripetal component. So centripetal component is equal to you can say omega square L by 2 over here, and this angle is theta. Okay, so this angle is going to be theta as well. So this and this angle is going to be theta as well over here. So now we can write the constraint relationship for the acceleration of point A in order to relate let's say this is a radial, let's write. So we can write it as the acceleration of point A will only be along the horizontal direction, and the vertical component of acceleration is going to be equal to 0. So that we can use as constraint relationship of point A. So that will be giving us like at, which is L by 2 alpha cos theta, plus sine component of this, so that would be AR, that is omega square L by 2 sine theta, must be equal to this AC over here. So this is AC, so that is basically equation number 1. And another two variables in this would be like one variable is AC and the another variable is alpha, and in the dynamics of this problem one variable is this normal. So three equation we are looking for. So one equation is the constraint equation, the another two equation we can write, one would be the equation of force and the another would be the equation of torque. So mg force is acting in downward direction. So this equation we can write in vertically downward direction. That would be mg minus n is equal to mass times acceleration of center of mass. So this is equation number 2. And we can write the equation of torque. But before writing the equation of torque, we need to figure out like about which axis we should write. So in the previous class also I said that it is always convenient to write down the equation of torque about an axis passing through center of mass, because even if the center of mass is accelerated, the pseudo force that will be passing through center of mass will not be producing any torque. So torque about let's write over here, torque about C. So torque about C is going to be, this is N, and its arm is going to be L by 2 cos theta. So the only torque will be due to normal. So that would be N times L by 2 cos theta over here. And that will be equal to moment of inertia of this rod about center of mass. So that is going to be ml square by 12 over here into alpha. Okay, so that is equation number 3. So we are having three unknowns and three equation. We can always solve for it. Okay, so today we have discussed the concept of combined translational and rotational motion. In next class I will be dealing with the conservation of angular momentum, uh, angular impulse momentum theorem, and we will start the discussion of the rolling motion over here in detail. Okay, so for today it is that's all. So thank you very much for joining us. Thank you.